Hello, everyone, and welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Rula Deeb. I'm a senior principal at Geosynta Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I have the pleasure today of facilitating this call. Our webinar will consist of a brief overview of SERDP and ESTCP, followed by technical content which details results from Department of Defense funded research to develop tools to enhance the resiliency of DoD infrastructure. We're going to start with Dr. Daniel Feldman from Lawrence Berkeley National Lab. Dan will describe an effort to translate projections of 21st century temperature and precipitation associated with future emission scenarios from dozens of climate modeling centers with the goal of identifying the risks that DoD facilities and infrastructure will face into the future. Dan's presentation will be followed by a short Q&A answer. Second, Professor Xixi Wang from Old Dominion University will discuss the development of an innovative approach for creating next-generation intensity, duration, frequency curves that consider non-stationary rainfall and can be used as a tool for the planning, design, and management of DoD's infrastructure. We will conclude the webinar with a longer interactive Q&A session with both of our speakers. On this slide, we have provided a few suggestions in case you experience technical difficulties with the broadcast platform. Firefox, IE, or Edge are the most compatible browsers to use. If for some reason you lose the content on your screen or if your screen freezes, try keying Control F5 to perform a hard refresh. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompt as they appear on your screen. If you continue to experience difficulties, please call into the conference line shown here. You may also submit a comment using the chat box. Please only use that chat box for comments related to technical difficulties. The Q&A option should be reserved for questions that we will pose to the speakers. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. Please feel free to submit questions well in advance of the Q&A sessions. And when submitting your questions, please make sure to add your organization name at the end of your question so that we can identify you during the Q&A sessions. With that, I would like to introduce Dr. Kurt Preston, who is the SERDP and ESTCP Program Manager for Resource Conservation and Resiliency. Dr. Preston has tracked his career between civilian, university, and military positions. Prior to his current position with SERDP and ESTCP, he was a faculty member and research administrator at the University of Nebraska-Lincoln, where he led faculty development efforts to improve research competitiveness. In this position, Kurt also worked with technology transfer personnel, academic departments, and colleges to build university research capability. In addition, Kurt has served as a member of Chief of the Army Corps of Engineers Environmental Advisory Board. Kurt?
Thank you, Rula. I'm happy to welcome everyone to today's SERDP and ESTCP webinar. SERDP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the Department of Defense, Department of Energy, and the Environmental Protection Agency. SERDP's mission is to identify and address high priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impacts the real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTC demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs, with much of SERDP research occurring in the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are four program areas in SERDP and 5 in ESTCP. The Installation in Energy and Water program is only found in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Resiliency, and Weapon Systems and Platforms, are found both in SERDP and ESTCP programs managed jointly by a designated program manager. Our webinar today is focusing on research and demonstrations that were conducted under the Resource Conservation and Resiliency program area, which has essentially 3 main areas of research: natural resources, resiliency, and wildland fire. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. As you can see, upcoming webinars will cover a broad range of topics, including managing contaminated sediments, accelerated corrosion and aging studies, treatment options for emerging contaminants in groundwater, and developing and demonstrating non-toxic paints for corrosion protection. The next 2 resource conservation webinars will be held on May 9th and June 20th, and will feature speakers on 2 topics: the role of soil microbial communities in ecosystem restoration, and developing adaptation strategies to address climate change and uncertainty. You can find additional information about upcoming webinars at this link. Registration is now live for webinars through the end of the year. I would like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. We would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at the end of the webcast. I am pleased to announce that the SERDP ESTCP Symposium will be held again this upcoming December in Washington, D.C. The 3-day event will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration information will be available soon on the SERDP and ESTC website. The symposium will be held as tradition the week after Thanksgiving. I hope you enjoy the webinar today.
Thank you so much, Kurt. And now it is my pleasure to introduce our first speaker, Dr. Daniel Feldman. Dan is a research scientist working in the Earth and Environmental Sciences Division at the Lawrence Berkeley National Lab in California. His research covers many aspects of atmospheric science, including fundamental radiative transfer and Earth system model intercomparison. More recently, his work has focused on hydroclimate science questions, and that led to his development of a range of plausible downscaled climate change scenarios for the California Department of Water Resources. Dan is also leading research to develop the modeling tools and observations needed to understand why Earth system models overpredict springtime snowmelt. Finally, he earned his bachelor's degree in environmental engineering science at MIT and his master's and doctoral degrees in environmental science and engineering from Caltech. Dan, please proceed.
Thanks so much, Rula. And I'd like to take this opportunity to thank SERDP and ESTCP for the opportunity to present today, and also wish all of you a happy Pi Day. I hope you are able to enjoy some pie and be rational the whole day. Anyways, I'll be talking about work that I and my co-authors have done as part of the SERDP SEED project. The title here is a bit of a mouthful, but it's really important that we understand how we can go from the coupled model intercomparison ensemble projections to really understand facility level risks and really understand where non-stationarity and temperature and precipitation distributions might affect this risk. So as the title of the presentation suggests, at a high level, we're building towards a capability to really help end users navigate through this coupled model intercomparison project, or CMIP, ensemble of climate model projections for the 21st century, to understand what they mean for the facility level changes in statistical distributions of temperature and precipitation. Okay, so just as a brief agenda here, first I'll present on what CMIP is currently and how it has been used. And then I'll talk about the things that CMIP models do well, and also discuss how they are, frankly, blunt instruments for developing projections at the DoD facility level. With that, I'll present an overview of a step-by-step approach that we have taken to go from course projections in the CMIP ensemble to facility level projections. And I'll note that the approach that we take for starters is fairly standard, but along the way, I'll discuss the need for caution with every step of this process. And in particular, I'll talk about model bias correction and present work from a co-author on how we actually need to be really cautious in how we interpret our observational record from weather stations to understand where models are underperforming. Next, I'll talk about the approaches from going from a spatial resolution of the order of 100 kilometers to a spatial resolution on the order of 5 or 6 kilometers. And this is conventionally referred to as downscaling. And statistical methods for this are conventionally utilized, but they necessarily have an implicit assumption of stationarity built in. And so I'll discuss the work that co-authors are doing to learn from a set of targeted experiments regarding both downscaling and about the model actually being downscaled, which we will refer to as the parent model. And then finally, I'll talk about the next phase of CMIP, which is CMIP 6, which will inform the IPCC 6th assessment report. And I'll talk about the challenges and opportunities that will likely arise from that quite large data set that is currently being developed. So first, though, I'd like to contextualize this research and discuss why it has relevance to the Department of Defense. As the climate changes, we may experience changes in the means and extremes of many quantities that directly and indirectly impact both infrastructure and operations. The focus of this project is on temperature and precipitation distributions. And I'd also like to note that a number of other sort of projects have shown and are investigating how changes in these distributions may impact, for example, sensitive ecosystems on DoD facilities. Changes in global average and global variability in temperature and precipitation are the subject of considerable research, but the global averages and global variability is really external to this project. It's really at the local level that we care about, and that's actually where there are definitely some challenges, and it is really the cutting or even bleeding edge here. This project is meant to aid the user community to navigate the complicated landscape of climate models, of which there are dozens, and translate those projections down to the scales of interest so that there's a credible mechanism to rank models and downscaling techniques. Ultimately, the temperature and precipitation information is used as inputs into a wide variety of applied models, including but certainly not limited to hydrological models to assess flooding risk. And these downstream models, so to speak, have challenges for incorporating potentially the uncertainty that might be upstream with the climate models and their downscaling techniques. So we really need to develop ranges of scenarios for these downstream models. Okay, so first of all, a discussion of the landscape of climate models. There have been several rounds or phases of the Coupled Model Intercomparison Project, or CMIP. CMIP exercises produce temperature and precipitation projections that are developed from dozens of climate model runs. These models run different experiments, including those that are forced with different emission scenarios. For the last phase of a CMIP, called CMIP 5, there were something called representative concentration pathways, or RCPs, that were standardized, and there were a number of RCPs roughly corresponding to the additional energy in watts per meter squared added to the atmosphere as the result of anthropogenic activities relative to the pre-industrial period. So RCP 8.5 is approximately 8.5 watts per meter squared of additional energy in the atmosphere associated with anthropogenic activity. The plot on the right here shows that the global average temperature anomaly for these models is a function of different emission scenarios. This is a bit of a spaghetti plot, but I'd point out that there's greater warming with greater input of energy in general, but there is definitely a large spread here. The models also run historical calculations where they attempt to reproduce the historical record. But how shall we make sense of this range in models? Is the model's skill over the historical record a guarantee of future skill? Conventionally, uncertainty is determined from a range in model results, but there are some complicating factors here. To the extent that the models share physical representations, there should be very little or no range in results, but where models share erroneous representations, parameterizations, things that are even unobservable, this can be a bit problematic, and this is an area of active research. Models can be weighted by their historical performance, and this was done with the recently released fourth National Climate Assessment. They developed a multivariate metric to discuss that considered surface temperature, precipitation, energy fluxes, and temperature and precipitation extremes, and so they rank ordered the models that way, but they also needed to recognize that the models are correlated, so that in the case of weighting models to produce an ensemble mean or ensemble range, we need to take into account that these are not necessarily independent models, and so they thought about different approaches to dealing with this, and I would point out that the figure on the right, the figure on the left shows the weighted multi-model mean change in mid-21st century temperature in degrees Fahrenheit when we take into account the historical performance and then the model independence, and then the model the plot on the right shows the mean of the three warmest models in CMIP 5, and we can see that there's about 4 degrees more warming with the warmest of the models in the Midwest, and so this kind of gives you a rough sense of kind of the spread and of the different ways that we can cut the multi-model ensemble. So again, I mentioned that there's, that it's important to take into account model independence, so that we're essentially not counting the same quantity twice when we perform our ensemble averages. And so this this plot from this recent paper on climate model evaluation noted that model skill, which is how well they reproduce the historical record, and independence are related, and I'd point out that there's really no point in the upper right quadrant of this figure here, and that's kind of a problem because it indicates that there's no model that's independent of all of the other models and exhibits lots of skill. Because if there were, that'd be great, and that would be the one we would kind of gravitate towards. Okay, so outside of these skill metrics, which are definitely of interest in their own right, we need to outline an approach to get to the relevant projections of temperature and precipitation. We start with climate model simulations and perform downscaling, which typically involves a historical approach. And so this is shown in this flow chart on the left-hand column. We evaluate the historical model against gridded observations, and these we have these weather station data, and we take it to gridded observations. And then we do a comparison to evaluate the skill of this of an individual downscaled model, and we note that there can often be, even in the historical record, fairly significant disagreement between the model and the gridded observations. And so typically, an approach that's used is to bias correct the historical model, which involves essentially shifting the model, the downscaled historical model results by a number so that it is consistent with the gridded observational product, and then looking at the relative change in a given quantity of temperature or precipitation, for example, between the model's historical and future projections, and then use that as a basis to develop facility level projections at the scale of a few kilometers. But this is a fairly standard approach, but it is important that we critically evaluate every step of the process. So first, I'm going to talk about the results when we take the standard approach, and then I'm going to talk about some critical evaluation. So briefly, what we did here is we bias corrected and downscaled a number of models using something called the localized constructed analogs approach, and we again weighted model performance based on historical performance and the independence of the models, essentially their error correlation structure. And then we produced a weighted model ensemble to develop precipitation and temperature distributions. Very briefly, I wanted to indicate with these plots that that the models in their historical performance are there's a range in their performance, and what I've shown up top here is the change in the 20-year daily maximum temperature return value between the end of the 20th century and the middle of the 21st century, and this is just derived from essentially weather station data, and so we can see a fingerprint pattern of this. There's a slight reduction in the 20-year maximum maximum temperature return value in the central part of the United States, and in the upper Midwest we see a slight increase. And then when we look at the bottom plots at 8 different climate models, they don't necessarily reproduce that pattern all that well. And in temperature, it's not quite as severe, but there's some changes in the southeastern United States in the daily precipitation return value at the 20-year level, and most of the models are actually a little bit better in this regard as compared to temperature. But anyway, so if we take the approach that I outlined in the process chain a few slides ago, and we can combine a set of the CMIP models and produce an estimated change in 20-year daily maximum return values for different emission scenarios. So the plot on the left shows the RCP 4.5 emission scenario, and the plot on the right shows the RCP 8.5 emission scenario. And we can, from these plots, you see that the daily maximum return value changes by a little over 3 degrees across most of the conterminous United States in the RCP 8.5 as compared to the RCP 4.5 scenario, which kind of gives you a sense of, okay, how much is the temperature, at least a temperature extreme going to increase as a function of different emission scenarios in the middle of the 21st century. The plot of precipitation is a little bit more complicated, and it shows that, again, in the Gulf Coast, southeastern United States, we see a bit more precipitation change in a return value, in the RCP 8.5 versus RCP 4.5 scenarios. But at a high level, we need to understand how much real confidence we can have in these projections, because what I discussed was a process chain that was, that there was, again, some need for caution. And so what I'm going to talk about now is some cutting-edge research that co-authors have done to revisit some key assumptions here. The first has to do with bias correction. So I mentioned that there was weather station data that was gridded and then compared against climate models under the historical record. This plot here shows the distribution of a wide variety of different weather stations that form the basis for the Global Historical Climatology Network and are the basis for the construction of the gridded product. Traditional methods to do this gridding are fairly would seem to be straightforward, either linear interpolation or distance weighting, or sometimes a little bit more fancy with kriging. But it's important to point out that, for example, when we're thinking about precipitation distributions, extreme precipitation is not spatially isotropic. It's actually, when you look at the station data information, which a co-author of mine did, they found that there's spatial anisotropy in extreme precipitation events. And so, so these plots here show show essentially the spatial correlation as a function of season for extreme precipitation. And so, if we do traditional gridding, this will spread out these extremes isotropically, as opposed to how they should be spread out anisotropically. And if we assume isotropy in the way that we do gridding, we will tend to underestimate extreme precipitation, even in the historical record. And so what these scatter plots show is the extent of the underestimation of precipitation extremes at the 20-year return value when we do traditional gridding on the x-axis versus when we do gridding where we take into account the fact that there is a spatial anisotropy. And this actually has a geographic characteristic to it as well. And this plot here shows that that we can see that in the southeastern United States and in the coastal West, that if we do not take into account spatial anisotropy for our gridding, that we will underestimate the 20-year return value in daily precipitation by over 28 millimeters. And then I should also point out that if we don't take into account basically the orographic distribution of orographic character of precipitation, we can see that we could actually overestimate the 20-year return value in precipitation in the Rockies. And so these kind of considerations are very important for when we actually create a gridded product to compare against observations, or sorry, to compare against the model. And this paper was recently released in Climate Dynamics by Mark Risser, co-author. So I also wanted to point out the key assumption, one of the other key assumptions is associated with downscaling. So climate model spatial resolution, the most fine climate models will have spatial resolutions on the scale of 100 square kilometers. Typically, they are actually much finer, or much coarser, more like 10,000 square kilometers. But again, any of those values are generally too coarse for local decision making. We need order of 25 or 50 square kilometers. And so a widely utilized approach is to use downscaling. For a wide variety of reasons, statistical methods are widely utilized. They develop analogous observational days in order to develop coarse-to-fine relationships between the model and the local scale, the model scale and the local scale. And in downscaling, at least with statistical methods, there is an implicit assumption of stationarity because they're built from a historical observational record and can't include climate change. So, sorry, hold on one second here. And so, so how problematic is this? So work from co-authors just found that if we look at the historical performance of a downscaling technique, for example, LOCA, and it compares quite favorably to a dynamical downscaling technique, which uses basically a model within the climate model to create a solution for what is going on at the fine scale. Over the historical record, things look pretty good, as shown on the left here, but on the right, at the end of the 21st century, the error actually triples for this specific climate model, which is the NRM-CM5 model. Similarly, the precipitation error doubles from the historical to the future scenario. So what is actually going on here? Is this a problem with the parent model, or downscaling, or some combo of the two? So a deeper dive is needed. So our co-authors, what they did is they looked at the raw GCM, and they found that the upper right shows the raw GCM change in April maximum temperature in the 21st century, and various different statistical downscaling techniques, ones that are trained under future analogs or trained in the past. And they show that it really actually isn't, the bottom three plots are fairly similar and indicate that are a function of different statistical methods, and indicate that really the statistical method isn't the issue, that it's really the fact that that the parent model is in error. The upper middle plot shows the solution with dynamical downscaling, which resolves the vertical profile of temperature much more accurately, and includes snow albedo effects. And really, it's the parent model is not actually resolving the Sierra and the snow albedo feedback correctly, and this crude representation is really just propagating into the downscaling techniques. And similarly, the model is not getting the temperature contrast between the Great Basin and the Gulf of California correctly. And so we can see in the upper center plot, there's a considerably different representation of changes in precipitation, especially across southeastern California, that's associated with improper representation in the model of the North American monsoon processes. And so so ordinarily dynamical downscaling is very computationally expensive, but it's important here because it helps reveal the error growth in space and time and why that actually is taking place. So ultimately, a deeper dive really is needed to understand how apparent errors in downscaling grow. For this specific model, coastal and mountain gradients were not well resolved, and these intercomparisons show that at least if we care about north-south gradients in California, that downscaling, dynamical downscaling is important. And ultimately, I would point out that the bias correction techniques that led to the apparent agreement during the historical record between different, between observations and the parent model's downscaled results, really sweep those errors under the rug, and those will tend to reemerge as in future projections if statistical methods are used. Okay, so ultimately, as we move into the next phase of CMIP, there's going to be a large number of different climate models that are going to be reporting different experiments. CMIP 6 has 20 to 40 petabytes in estimated volume, although these data are still coming down the pipeline, so we'll see exactly what comes out of it. But there are a wide variety of different experiments, including regional downscaling experiments, CORDEX, and high-resolution model and comparisons that will allow us to look more closely at the model and its process representation. And these can help reveal whether or not the coarse models are appropriate for being downscaled to estimate the GOD facility level risk, and really what a stationarity assumptions mean for the risk that these facilities face. So in conclusion, the take-home messages here are that there's a lot of different climate models, and we need to be very careful in how we go from the coarse climate models to facility level risk. And we can definitely take an approach where we weight historical models by their historical performance and their independence from each other. But we need to exercise caution every step of the way, especially in terms of how we utilize gridding, for example, for extreme precipitation, and how different downscaling techniques are used to make sure that basically the errors that are in the parent model don't reemerge under climate change. CMIP 6 is an exciting development, and we'll see what happens with that as many different modeling centers, including some new ones, report new results. I'd also like to acknowledge the many co-authors that have contributed to this presentation, and would like to point to this link and take any questions as they become available. Thank you.
Great, thank you so much, Daniel. I would like to remind you that you may submit questions by using the Q&A box on your screen. Only use the chat box to report technical difficulties. So again, we did receive a number of questions for you. The first one is from Kansas State University. How was the spatial correlation between extreme events determined?
Right, so that's a great question. That is determined from the development of a geostatistical model that has essentially an XY correlation function. These are produced from the raw data that are reported to the Global Historical Climatology Network, and those data are I guess we don't use the -999s in the data set, but when the stations are reporting data, we develop correlation functions and then utilize those as a basis for developing what we refer to as a probabilistic gridded product. I would also point out that there's a paper in Climate Dynamics that hopefully I can send out a link to, so that you can see all of the details, because it is a bit involved about how to actually construct this model.
Great, thank you so much. Here's a question from the North Carolina State Climate Office. Mm-hmm. Are there any risks in assuming the dynamically downscaled result is correct?
Absolutely, and that's a really great point, and I'm glad that this was brought up. Dynamical downscaling is not error-free. There's lots of parameterizations associated with, for example, the WRF model we used here for downscaling. At a kind of a high level, there is, the dynamical downscaling model there is to a lesser extent, but still to non-zero extent, the stationarity built into that, because it has been constructed based on historical observations, and although it does have physical mechanisms built into it. Ultimately, it's important we can look at different dynamical downscaling solutions that might help reveal whether or not those parameterizations within those models are of concern. But we can also look at the historical record. So one nice thing that we have recently noticed is that some of these downscaling solutions were not the training kind of ended a few years ago, and there's been some extreme events that have taken place, and we can kind of start to look at at whether or not the downscaling solutions from a dynamical approach are really diverging from observations, and kind of point towards the process representation errors in those models as well. So that's that is definitely an important point, and it's something that I think intercomparisons with careful analysis will help reveal.
Great, thank you. Here's a question from Oregon State University. Why are the model's precipitation increases so spatially clustered, especially in the southeast of the United States?
Right. So, I mean, I think that is so. What I was showing in the let's see slide. So the comparisons and changes in return values are associated with these are extreme precipitation events, and so they're typically associated with things like tropical cyclones, things like that. So that will there's certainly a lot of this is an active area of research about how those will change under climate change. But what I've shown here is at least the ensemble of models, their description of how those events are changing, at least relative to their historical performance with respect mostly from tropical cyclones.
Great, thank you so much. A question from George Mason University. Can you elaborate a little more on the dynamic downscaling method and what physical methods are built into it?
Sure. So the dynamical downscaling method that the co-authors here used was based on matching, essentially forcing a regional model, in this case, weather research and forecasting model, with the conditions that are set at the regional level by the climate model. So, what I was showing was CNRM, CM5. So, essentially outside of California, we create these boundary conditions for WRF to be run. WRF is an atmospheric process model, and so it provides solutions based on conservation equations, and but there are lots of parameterizations built into that, and so so boundary layer schemes and convective parameterizations are all part of WRF as it attempts to create a solution at the fine scale. WRF can be run down to resolutions of a few hundred meters, but the processes that that still obscures a number of eddy and microphysical processes that are potentially important. But yeah, so that's kind of at sort of a basic level what WRF is up to. There are other atmospheric process models that can be utilized within the the context of downscaling. And there's also it's kind of an active area of research about how to match the dynamical downscaling with the parent climate model, so that you're not, for example, at the boundaries, creating or destroying energy or mass. But at a high level, it's important to think about resolving the physics at some basic aspects of the physics, for example, orographic effects and things like that are much more difficult to resolve, or at least represent in a coarse scale model than what we see when we have a fine scale model like WRF.
Great. Thank you so much. We have several more questions that came for you. We'll reserve them for the final Q&A session. At this point, I would like to introduce our second speaker, Dr. Xixi Wang. Xixi is an associate professor of civil and environmental engineering at Old Dominion University in Norfolk, Virginia. Prior to this, he held positions as an assistant professor at Tarleton State University, a research scientist at the University of North Dakota, a civil engineer at Michael Baker Jr., and an assistant professor at Tsinghua University. Xixi's current research focuses on the effects of climate change and human activity on water resources, water-soil vegetation nexus and equilibrium with changing climate, and watershed hydrology and stormwater management. He earned his doctoral degree in agricultural engineering from Iowa State University. Dr. Wang, please proceed.
Okay. First, I want to appreciate this opportunity to share my preliminary research results with everybody here. So the title of the presentation is Next Generation Rainfall ADF Curves from for the Virginia drainage area of Chesapeake Bay. First, I will have a brief introduction about what are ADF curves and why do we need ADF curves. Then summarize the benefits to DoD or other people. And then I will talk about this research goals and objectives. And also I will clarify some about the differences between historical and next generation ADF curves. Because some people may think we have been using ADF curves for years. Why do we need the next generation ADF curves? What are the differences between historical and next generation ADF curves? Then I will talk about the approach we developed for this research. Then I talk about this little bit about this study site and the data we used. Then I will introduce the methods, then summarize the results and draw some conclusions. So first the question, what are the ADF curves? ADF stands for intensity duration frequency curve. So ADF curve defines the relationship between these two. Intensity that refers to rainfall per unit time. For example, we can measure this inch power, millimeter power, something like that. Duration, that's a lasting time of a rainfall event. That could be 30 minutes, 40 minutes, and most time in engineering applications, we like to use 24 hours, something like that. Then frequency, that's a percent chance to occur for an event. So in practice, we like to use another terminology that's called the return period. This is just a reciprocal of frequency. Because it is convenient to use the return period rather than frequency, maybe talk to general public. For example, this graph shows an example of this ADF curve. So this x-axis, that's the duration. Y-axis, that's the intensity. Then this is labeled for different return period. That's a 2-year, 5-year. Probably you are familiar with these terminologies because we can hear these terminologies from weather forecasting or from some consulting engineers. They mention, oh, this structure designed for 50-year storm or 10-year storm, something like that. So some people say, why do we need to have these ADF curves? In fact, the ADF curves have lots of practical applications. For example, there's a flood forecasting. They might need to tell people, oh, this year we've got a 100-year flood, or something like that. Or also the management, flood management. So FEMA, that's a Federal Emergency Management Agency. So they developed this flood insurance map, so that delineates this 100-year flood boundary, so that people can evaluate the risk of their properties. Also, ADF curves are used for planning and design of various kinds of engineered structures, like drainage system, dike, levees. So we use this kind of ADF curves to determine the size of this kind of structure. For example, this city drainage system, we can say for important area, we will use this 50-year storm to size the drainage pipeline, the storm sewer system. So ADF curves have a lot of practical applications and also very close to us, very close to everybody. Then why do we need to have next generation ADF curves? Because of the climate change, we are experiencing significant changes in rainfall characteristics. Probably in the past, we have more storms in more season, and right now we have this same amount of storms in another season. Timing could be changed, and magnitude could be changed. So this could cause the changes to these ADF curves. And also, this historical ADF curves did not consider stationarity. Assume the stationarity. That's cannot assume this non-stationarity. Infrastructure can be over or other designed if wrong ADF curves are used. That's why we need to have this next generation ADF curves, but currently we are lacking this kind of product tools. What are the benefits to DoD? First, next generation ADF curves can help DoD acknowledge uncertainties resulting from climate non-stationarity. That's overall, that's climate change. What uncertainties could be resulted from this kind of changes. Also, this can help DoD consider uncertainties in planning stage of some structures. Before this infrastructure was constructed, so this needed to consider these uncertainties. Also can help design the ongoing structures, also the management of existing structures. So you can see ADF curves are always needed from the beginning to the end to the management of the structures. Finally, this can help guard against over and other competing resources. So that's pretty important because our resources are always limited. So we want to use these resources in the best way. So this next generation ADF curves could help us avoid this kind of over or other competing these resources. So the research goals include this advanced understanding of climate non-stationarity. Also improve infrastructure planning, design, and management. For this particular research project, we wanted to develop an approach for creating probability-based ADF curves. Also use this approach to create next generation ADF curves for entire Virginia. So this is a comparison between the two types of ADF curves. The left side, that's historical ADF curves. So you can see this kind of curves usually developed using observed historical rainfall data. It is deterministic. That means for a given duration and a given return period, you will have only one intensity. So for example, this duration 10 minutes, and for 2-year return period, there's only one value here. That's roughly probably 34 millimeter per hour. Also, this historical ADF curves only assume stationary climate. On the other hand, this right side, that's the next generation ADF curves. So these kind of curves need to be developed using observed and predicted them. Usually, that's probably RCM, regional climate model, needed to be used to predict the future precipitation rainfall. Also, these curves are probability based. That means for a given duration and the time period, for example, assume this 10 minutes duration. And for this same 2 year, usually you have a range of this rainfall intensity. That's for this example, that's from the 20 to probably 44 millimeter per hour. And for each value of this rainfall intensity, it has an associated probability. So for example, this 34, that's probably 34 probability is roughly 80%. So this is probability based. So usually we will have a range of intensities for given duration and return period. These kind of curves considers non-stationary climate. That's consider the future uncertainties of this climate variations. So the overall approach developed in this project can be shown in this flow chart. So this right side, that's a station level, that's a gauge level. So we started from this observed 15 minutes precipitation data. That's downloaded from the National Climate Center. Then we formulate this stationary level data sets of this observed duration of precipitation. Because it started from 15 minutes, we can accumulate together 30 minutes, 45 minutes, and so on. Then select the best station level distribution. We need to determine the best statistical distribution for this data set. Then we use this best distribution to create this station level existing ADF curves. This right side, this for future. So we use this projected precipitation data. So usually that's a very good product from North American Regional Climate Change Assessment Program. So they have very good product there. So we use this product. That's a spatial resolution of 50 kilometers, temporal scale. That's 3 hours. But we need to downscale. We need to do this spatial downscale. So we need to downscale this grid scale precipitation projected by this RCM models to this gauge level or station level. Also, we need to disaggregate the data to this short duration. That's 15 minutes. There we can get 30 minutes, 45 minutes. Then we formulate this station level data sets for projected duration of precipitation. Then we can use this best distribution determined here to create the station level future ADF curves. So this is station level ADF curves. That's a historical ADF curves and also this next generation ADF curves. For watershed level, so we need to have this different data sets. That's typically that's a national hydrograph data set from USGS, define the boundaries of watershed. Then we use these Titan polygons to subdivide this watershed into smaller areas that are controlled by each gauge stations. Then we formulate this watershed level data sets. So that's needed to do this weighted average of this station level precipitation to get this watershed level precipitation data sets. Then we need to select this watershed level distribution and create this watershed level ADF curves. So that's an overall approach we developed and used in this research. So this study site, that's entire Virginia, which most of Virginia is located within Chesapeake Bay watershed. So this is Chesapeake Bay watershed that's spanning from New York until Virginia here. So this map shows climatic divisions. So in Virginia, that has 6 climatic divisions. Also shows these physiographic divisions. So that's 5 physiographic divisions. We overlaid these 2 maps to define these climatic physiographic zones. Finally, we got these 13 zones, 13 climatic physiographic zones. Then the study was conducted for each of the zones. So that means we treat each of these zones as a basic unit. We assume within each of the zones, the climate is uniform. So that's our basic analysis unit. So the data used include national hydrograph dataset. That's downloaded from USGS. Also, we use the 15 minutes precipitation data from 57 rain gauges. So this data were downloaded from National Climate Data Center. Also, we use the projections from 12 RCM, GCM models, so regional climate model, there's generalized circulation models. So the data have a spatial scale of 15 kilometers and 3-hour temporal scales. So the methods, first we need to fill missing values because most of the stations have missing values from probably days to months. So we need to find the best way to fill these missing values. So we use the various kinds of geostatistical methods to fill the missing values. Then we need to detect this trend and the non-stationarity of the precipitation. So we use the modified Mach candle to detect trend, and also we use the cumulative deviation method to detect this non-stationarity of precipitation. For this best statistical distribution, we use the 3 candidate distributions. One is the Gamble, another is the Fairchild, another Weibull. So these 3 methods are widely used. So we, based on this observed precipitation data, we select the best distribution for each of the gauges. Then we did this spatial downscaling and temporal downscaling of this climate model predictions. Then we create these ADF curves that include gauge level historical, watershed level historical, gauge level probability based, and watershed level probability based. Non-stationarity tested on cumulative deviations from overall. So that's I mentioned on the last slide. This is a better distribution, so was selected based on visualization plots and also based on this case test. So we used this candle test and the visualization plot to select the best distribution. For this spatial downscaling, we used 4 grids around the gauge. There's different climate models have different grids. So we use we use 4 grids surrounding a gauge to do this spatial downscaling. For this temporal downscaling, we used this regression method. That's a statistical method. So we regressed over this 3-hour precipitation. We got these regression equations, bias correction factors. Then we did this temporal downscaling. Types of polygons were used to calculate area precipitation for each watershed. So this summary of the results. First, the trend and non-stationarity. We found 11 gauges had significant decrease in trend of intensity. Annual decrease in trend rate ranges from roughly 0.01 to 2.54 millimeter per hour. So intensity had this significant decrease in trend at these 11 gauges. But the 1 gauge had a significant increase in trend. No step changes were detected for all gauges. But the intensities had a significant decrease in trend, but the variation, that's the interannual variation of precipitation, tended to decrease. So that means this overall runoff volume could be large. Probably the total precipitation tended to increase, but the intensities tended to decrease. So if we use historical ADF curves to design structures, then the structure could be oversized for peak controlled structures like a pipeline, storm sewer pipeline. So that could be oversized. But for volume controlled structures like a detention pond, that could be undersized. So this graph shows this trend for different durational intensities. So this one, that's 15 minutes at this station. So you can see this significant decrease in trend of this 15 minutes intensity. With the increase of these durations, the decrease in trend becomes smaller. So this is a 48-hour duration. So you can see this trend is not as significant as this 15 minutes. So 15 minutes is a very significant decrease in trend. Also, for a shorter duration, the decreasing rate is large. Please remember that we detected this decreasing trend. Decreasing rate ranges from 0.01 to 2.54 millimeter per hour. So for a shorter duration, this decreasing rate is larger than a larger duration. So these are best distributions. We found 30 gauges have a best distribution or gamble. Gamble is best distribution for 30 gauges. Variable is best distribution for 23 gauges. But for 4 gauges, either gamble or variable could be good because we couldn't differentiate these two distributions based on case test and visualization part for these 4 gauges. So this is just the example of this visualization part for these different distributions. So this one, that's stars that shows this empirical values, empirical exceedance probability for this durational intensity. And this one, that's a red line that shows the gamble distribution. If you fit the gamble distribution, so that's how this is close to this empirical value. And this one, that's blue, that's for variable distribution. And based on case test, so this for this station, gamble is best. And for this station, variable is best. So this shows the example of this gauge level historical ADF curves. So this, so if we compared these ADF curves with NOAA point precipitation frequency estimates. So this our ADF curves, that are historical ADF curves, are comparable with PPFEs for durations larger than 1 hour. So that means if your duration is larger, this difference is smaller. That's very similar with the NOAA PPFE curve. But for duration smaller than 1 hour, these historical ADF curves will give you larger intensity than the PPFE curves. For a larger return period, that's a big storm, that's a larger return period, that means a larger storm. So for larger storm, the difference between historical ADF curve and NOAA PPFEs tended to be large. So this is for this larger return period, that's the difference could be large. This example for this watershed level historical ADF curves. So first, we need to determine the best distribution for each watershed. So that's based on these control gauges, rain gauges. So we determine this best distribution for a given watershed based on this largest area, as a largest area controlled by this gauge. For example, let's look at this one. So this watershed is controlled by two gauges. So these are two gauges, and this gauge controls 933 square kilometers. This controls 501 square kilometers, and this has a best distribution variable / gamble. So that's either one is good. So we choose this as variable best distribution for this watershed. So we did the same thing for other watersheds. So this is just an example of this results for this historical ADF curves for this watershed. So that's a HAC number. That's a hydraulic catalog unit number, 8 digits. And this is for this watershed. So we got this ADF curves. So for spatial downscaling, so for each climatic physiographic zone, so we developed these regression equations between this projected 3-hour precipitation versus this observed 3-hour precipitation. So you can see this correlation is very good. That's a coefficient of determination. That's at least 0.7, about 0.7, most probably 0.9, something like that. So next step, we will use this one to downscale the projected data. And this one for temporal downscaling. So we established the relationship between 3-hour precipitation versus 15 minutes. This is 30 minutes, 45 minutes for each zone. So that's for each climatic physiographic zone. So you can see this not a very poor. That's a very good. That's a very good correlation. So next generation ADF curves. So currently we are other way to develop this next generation ADF curves. So finally we will have this ADF curves for 57 gauges, 53 watersheds. Durations include 15, 30, 45 minutes until this is 72 hours. So it's 1, 2, 3 until 72 hours. Return periods that include this commonly used return periods. Probably this USA most time we use is less than 100 a year, and sometimes we use 500 a year. For example, FEMA also delineate boundaries for this 500 a year. Totally, we will have this roughly 1,210 sets of ADF curves to be developed. So that's calculated 11 durations. That's 57 gauges there for plus 53 watersheds. Totally, we will have 1,210 sets of these curves to be developed. Then I will draw a little bit of conclusion here. First, we developed the approach for next generation ADF curves. So I showed you this overall approach, that's a flow chart. Also, we have a lot of detailed equations, formulas, so that's too complicated to be included on this slide. Also, we detected non-stationarity and sequence trap in Divergence. We created gauge level and watershed level historical ADF curves. So we are creating probability-based ADF curves. So I think this all of you can learn something that's practical to consider this non-stationarity for engineering design or management of your structures. Finally, we will deliver a tool for resilient design for DOD installations. So that's my contact information. Take your questions. Thank you very much.
Great, thank you so much, Xixi. We've received a number of questions for you. So we're gonna go ahead and get started here. This is another question from the North Carolina State Climate Office. How much of the non-stationarity is associated with intrinsic climate variability as opposed to anthropogenic climate change?
I think this non-stationarity is mainly related to climate change. Variability will not cause non-stationarity issue. Variability, that's 1 year could be larger, another year smaller, then probably next year will be larger again. So this will not cause non-stationarity issue.
Great, thank you. And here's another question from Texas A&M University. Since climate change-driven non-stationarity should occur on a large spatial scale, did you consider aggregating data from multiple stations before identifying or quantifying non-stationarity?
Yes, we did it. I mentioned that we subdivided Virginia into 13 climatic physiographic zones. So we did this analysis for each of the zones.
Great, thank you. And this is a question from Carnegie Mellon University. How is the rainfall coverage forecasted for regional analysis by using IDF curves?
So ADF curves are traditionally used for engineering scale. So that means we use these curves to design, manage our structures. Also, we can use this one to manage this water sources at the watershed level. For regional level, we could upscale, but we need to consider some covariances of this non-stationarity. But once the scale is larger, the spatial covariance correlation may become stronger.
Great, thank you. And this is a question from North Carolina State University. What method did you use to go from 50-kilometer NAR CCAP to the station level?
So we used the statistical downscaling method.
Great. And then one last question before we pull Dan back in. What types of data, if you were to summarize it and leave our audience with clear information on the type of data needed to develop probability-based IDF curves?
So we need to have this observed data rainfall with a short duration, such as 15 minutes. So if we don't have this kind of data, that's hard. Also, we need to have climate models predictions of future precipitation. So we need to use both observed historical rainfall data with a short duration and also climate model predicted data for the future.
Great, thank you. And Daniel, we'd love to pull you back in. So I'm going to ask you guys some questions, and if we can start off with you, Daniel, with the first response, and then we'll ask Xixi to weigh in on this, on these types of questions that are more general in nature. So Dan, as updates to climate models become available, how can we integrate this information into next generation IDF curves?
Right.
So this is a question. Okay.
Go on, Xixi. Oh, well, okay. So I guess I would say that you know, as these updates become available, you know, they really form forcing mechanisms for you know, for the creation of these next generation IDF curves. So it's really, you know, I guess how I see it, and I appreciate the perspective of Dr. Wang here. But how I see it is that, you know, we have these next generation climate models. We evaluate them for their process representations. We think about the types of downscaling that are appropriate, and then use those within the framework that that Dr. Wang has created to understand really what they mean at you know, from a physical infrastructure perspective.
Thank you. And Xixi, would you like to add anything?
Yes, for this one, I think currently we are considering use 12 climate model predictions. But as Dan mentioned, there are so many uncertainties needed to be addressed, in particular during this downscaling process. So probably we can have a good exchange after this presentation. I will have good exchange with Dan to see which method is best for this downscaling.
Great, thank you. And another question, Dan, and we'll start with you. Are the existing models, in your opinion, accurate enough in specific predictions of the timing of historical precipitation events?
Yeah, this is another great question. I would say that it's so with respect to the climate model projections, I think the best that can be said of them is that, you know, they provide you know, probabilistic projections, and so we shouldn't consider them as saying that, you know, in, you know, 2035 on you know, March 14th it's going to rain, or, you know, at a certain time, but we can think of them as saying, well, you know, that they can, you know, with a good degree of certainty, predict that at a high level, global average precipitation will change as a function of changes in temperature. There's a good theoretical basis for that now, and that you know, that storm tracks will move. There's also a good theoretical basis and a modeling basis for that, and you know, that certain types of, you know, events will shift in their nature, and you know, that as you know, so at the sort of regional level, I think we can have not quite as much confidence, but at least, you know, some. And then as we get to the more granular level, that's where you know, that's where more caution must be exercised.
Thank you so much. And Xixi, would you like something to add?
Yeah, these are very important when we determine this maximum intensities. So probably I'm thinking probably during a year, if this timing is not predicted accurately, can we just consider the magnitude? We focus on this total precipitation or maximum rainfall intensity rather than time, because we need to, when we do this downscaling, we need to correlate this predicted precipitation with the historical precipitation. So if we can't predict this timing accurately, probably we could just correlate, find a way to find a relationship between magnitude rather than time. And probably Dan has a
I mean, I did also want to point, that's a great point, Xixi, and I also wanted to point out that, you know, that there's been some discussions about, you know, when it you know, with respect to timing of you know, so onsets of seasons and things like that, and those are slightly different questions from, sort of a deterministic perspective. Those are also, probabilistic in nature. And so we can, develop tests and for things like, seasonal onsets and of certain quantities. So timing is, again, can be probabilistic in nature, and we can, start to develop tests and really just, again, looking at the processes that are contributing to those, specific timing of events is really important. And just to step back and say, well, is, kind of at a coarse scale, is the models, kind of set up in such a way that it can get those timings right. So for example, in California, depending on, so coastal fog is something that's, really a big deal in Northern California. And, that's a function of, gradients in temperature between coastal and inland areas. And so if, that kind of understanding of that sort of process, the processes that really, pull fog in from off the ocean is important. And if the model doesn't really have that, then it's, we can't really have all that much confidence in it. And so, so we can't really have all that much confidence in the, the onset of, of fog events in the future, and, whether or not those will dissipate and the timing of those with respect to seasons and things like that. But if the model does have gets that approximately right, then I think we can have conversely a bit more confidence in sort of its projections of how those processes will change, and then will ultimately affect the things that we care about.
Wonderful. Well, thank you both for a very informative webinar. As a reminder, our next event is on Thursday, April 11. Dr. Vernier Lohman from the University of Rhode Island and Dr. Kevin Sowers from the University of Maryland will discuss their work on managing contaminated sediments in the SERDP and ESTCP environmental restoration area. Registration is open for this webinar, so please visit the webinar webpage to register for this and other 2019 webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it if you could please take just a few moments to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you so much for your time.